Okay, so what do we see? What do you observations that you see in the either one, black or white? What are observations that you see?
A lot of people got 3.
Mm-hmm. A lot of people got 3. A lot of people got 3 up here, right? With the 5. When you guys flip the coin 5 times, a lot of people got 3s. Does that make sense?
Sure.
Why does it make sense?
50% was 5. It's about 50%.
There's a 50% chance of you getting a tails, right? And 3 is closest to 50. 2 and 3 are closest to 50%, right? You can't get 2.5 tails, right? So it's close. So it's extreme. So that makes sense, right? So down here, the whites. What do we see here? What's different here? Or what's different, same? What kind of observation over there? More spread out. More spread out. Mm-hmm. Does that make sense that it would be more spread out? Which one would we expect to be more spread out? The 5 times or the 20 times? You'd expect the 20 times to be more spread out?
Yeah.
Why?
Because you do it.
You do it more. So if you do it more, what happens? More data to record. So that means it's going to be, okay. Here's my question. What do we say? What's the probability that I flip a coin and get heads? 50%, right? So how come only 2 people got 50% here for the 20?
So that's perfect. We don't have perfect odds. It's like physics.
So here's my question. Why do we say there's a 50% chance of me getting heads or tails if it's around 50? Shouldn't we say it's about 50% chance? No one says that, right? We always, it's 50% chance that you're going to get heads or tails if you flip a coin once. Okay. So my question is, what happens to, are the other white sides, the 2 whites, are those wrong? No, they're not wrong, right? You guys flip the coin. But what does that explain? How does that explain? How can we explain the ones that aren't exactly 50%?
We just 50% chance what to get your body flipping.
No, what we're getting at, is the key. Listen up. What we're getting at is the key reason why people gamble or don't gamble is right here. There's no guarantees. Obviously, there's no guarantees. It's a game of chance, right? Isn't the flipping a coin just chance? So if it's 50%, it should be 10 out of 20, and then between 2 and 3, right? As we said, between 2 and 3. Well, up made sense, right? There it's you have a lot of data between 2 and 3. Here you have 2 out of 11 have 10, have perfect 50. So my question is again, why is it a 50% chance of me getting a tails? There's only 2 odds. That's why we say it, right? Does that prove it? Only 2 people out of 11 got what you said was the probability?
50% chance of getting tails, and then you get 50% of tails 20 times, which means each individual flip is 50% chance to get tails. Not 50% of all flips is tails.
Oh, okay. So if I flip a coin once, it's not a 50% chance I get a tails.
No, each individual flip is 50%, but not 50% of the entire data. It's going to be half tails and half tails.
Okay. So, because how do I show this to a person? A person's like 50% chance. There's a 50% chance that I get a tails, but then they look and say, well, why aren't those 10? I know where you got 50 because it's 2 sides, right? But why isn't it 10? What do you, what can you rephrase what he said?
He basically said that every single time you flip that coin, you're rolling, which means that if you do it 10 times, you're not guaranteed to have like a 5-5 split. Every time you flip that coin, it's 50% tails. So if I flip it 2 times, for example, one time it ends up being tails, one time it could be heads. If I flip it 3 times, it's gonna have a 2 split, or it can be all 3 on one side.
Okay.
It's a 50 probability.
So it's a 50% probability. You guys are kind of dancing around what's going on here. Here's the answer. It's on the next slide. Look at these down here.
Yep.
They did exactly what you did, except they did 20 tosses, I think 20 tosses, and they did heads. So one person on the first toss, they got no heads. Second toss, they got a heads. And then, so what are you seeing with these dots? So, it's not a perfect pattern. So if it's not a perfect pattern, what can we say about it? It's what?
Random.
It's random, or what else? What other words could we use? That's right. I'm not saying you're wrong. I'm just saying what other words could we use? What other words can we use? No one can think of any other words. I think some of you can, you just don't want to say it. Random. What else? What is a synonym for random? What was that? No, not that's not a synonym. There you go. That's what I was looking for. Unpredictable. See, I knew someone had it. They were being quiet. Yeah, don't be quiet. Say it. Don't let the same 3 people talk the whole time. So unpredictable, right? They're unpredictable, right? We can't predict. So if I flip a coin once, I'm not going to put money on it. If I flip a coin twice and someone says, hey, if you get 2 heads in a row, if you get a heads and a heads, if you get a heads and a tails, I'm not going to put money on that because it's unpredictable. But look over here. What's happening over here? Same thing is happening. Flipping a coin, number of heads. But how is this one different? So what Armin said is unpredictable for the last one. Would you say this one's unpredictable?
Yeah.
What's showing that's unpredictable? You consider that up and down?
It's very zoomed out. So like, oh yeah, if you know, it's extrapolated.
Okay, so let's go again. Unpredictable, right? Okay. So look at this picture, everyone. Everyone look at this picture. Mariana, can you see this picture? Okay, look at the picture. Now that's unpredictable. We say this is a definition of unpredictable. It's more predictable, right? It's more predictable, yeah. And I stopped at 500. The person who did this stopped at 500 tosses, right? What if they did 1,000 tosses? Or what if we had more students in here? What if we had double the amount of students and you guys did it the same, right? Up here represents about, it's about a little over 200, right? Up here was about 5 times, about 60, right? 60 tosses. What if we did 500, 1,000, 10,000 tosses? Are we still in that unpredictable area? What's happening? There you go, right? And what is that actual? There you go. That's why if I flip a coin, it's a 50% chance that I get heads or tails. Not because it has 2 sides, obviously, but the data has to back it up, right? The data has to back it up. That data don't back it up right here. These whites, Don't back it up. Okay. Why do we say that? Because we use a word. It's called, where is it? Right here, or a phrase. Law of large numbers says the more we do something, the answer will appear. The more we do something, the answer will appear. True probability. The true probability, right? The more we replicate it, the more we replicate what we were doing, right? Isn't the answer starting to appear here? Right? Just like Kuldeep said, the answer is starting to appear. It's 50%. And I stopped at 500. Can you imagine if I did it 1,000 times? Would there be any little, right? We started going like this. And then I'm doing this. And then I'm doing this. And then my fingers barely moving at all. Right? If we did it 1,000 times, it would be pretty straight. What if we did it 1,000,000 times? If this was a patient, what would happen to them? They'd be dead. They would be dead because it would be a straight line, right? That's why we say the probability. So when I talked about gambling, what does this have to do with gambling? Anybody who gambles, the reason they gamble is because why? I would argue with being fun, but why do they gamble? That's not the reason they gamble. They gamble because why? The thrill of they could win, right? They could win, right? I don't know of anyone who says, yay, money, throw it away. Throw it away. It's fun. There's always that thrill of winning, right? You could win a whole bunch of money. You could go home with a car, right? You could go home with all that stuff. That's the thrill, right? What they don't know is this. The more you do something, the more you're going to lose. The probability that you win any casino game, it's against you. It's against you, right? If I walk in and play one game one time, it's very unpredictable what's going to happen, right? Unpredictable what's going to happen. But if I sit there and play, come the next day and play, keep playing, I'm over here. It's not unpredictable. The casino knows exactly what I'm going to do. I'm going to lose the more I play, right? Because the casino knows the probability. It's not a 50, so the casino games aren't 50-50. 50% probability I win, 50% probability they win. It's way down here. It's not rigged. It's not rigged. Why is it not rigged? If it were rigged, that'd be against the law and they'd be out of business. I've never heard of a casino being shut down, but I mean, illegal casinos, sure. But I'm talking about legit Chancey, Table Mountain, Las Vegas, those big casinos, right? Those legal establishments. See, people think they're rigged. They're rigged. No, they're not rigged. They just know the probability. The probability of you winning is very low. If you don't know that going in, I'm sorry. You know, it's everywhere. The probability of you winning very low. But someone goes in and they play once. And what do you say about the probability early on? Unpredictable, very unpredictable, right? So you go in once and you win. Oh, I won, yeah, right? And I go tell everyone I know I won. And then that person comes in, next person comes in, and they lose, and they keep losing, And maybe they win down here, but it's not that big of a deal because how much have they lost already, right? The casino's like, hey, we'll give you $2,000 because guess what? You've already spent $10,000 over the course of a year, right? So they put their name on a board and say, look at this person. This person won $100,000. They'll do that every time. You know why? Because for every one of that person, they made millions from the people who lost, right? That's what casino knows. So anyone who gambles, that's why I don't gamble, because I know the math. It's not fun. You know, I mean, I'd literally have more fun taking out money and setting it on fire. That's more fun to me, right? Because that's essentially what you're doing when you gamble, okay? Now, there are a lot of people who have a lot of money and they can do what they want. You can do it. It's America. You can do what you want. But I'm just saying, I don't gamble for the reason this here. Because let's say I go in and play a casino game one time. I walk into Chansey, I put my money down, and I play one time, right? It's very unstable what's going to happen, right? I could win, I could lose, and then I walk out, right? Well, guess what? There are thousands of me. So even if I only play one time, and all of them play only one time, that's 1,000 times played. And what's going to happen out here? They know what's going to happen, right? So it's not rigged. They just know what's going to happen, right? And anyone who knows anything about probability knows what's going to happen. You know the end of the story. You just choose to play along, right? So it's not rigged. It's just the cards are against you. The cards are against you, literally. Okay, you're stacked against you. So when you do that, so that's why, because people see in here, right? In here, this instability. Drive down Shaw, you'll see signs, billboards, $100,000 I won a new car, I won this, I won that. It's true they did. But what you're not seeing is the thousands of people who went in and lost, right? So I'll give this person a $75,000 car, because guess what? From that same game, I got millions of people to lose, right? So it's worth it. It's worth it in the end. That's what the casino knows. And we'll talk about how to find probability for casino games, because probability, it's kind of sad, but the reason probability is a thing is because people who gamble created probabilities. They created probabilities because they want to know, what are the chances I'm going to win? What are the chances I'm going to lose? They want to know those things. So the reason why we teach probability is because, not because of gambling, but because it was created by people who gamble. Okay.
I can blame addicts for chapter 5.
You can blame what?
I can blame like gambling addicts for chapter 5. You wouldn't have chapter 5 if you didn't have gambling addicts.
Kind of, yeah. Kind of.
We shut down casino addicts, they are enthusiasts.
How many detectives
Right?
how many detectives do you have this one?
You're just not supposed to win.
Exactly. Exactly. Well, it's like saying this. It's like giving you a die and saying, okay, if you roll a 1, you win. If you roll a 2, 3, 4, 5, or 6, I win. And you're like, okay, is that a rigged game? Is that a rigged game? No, you just, the person was just not thinking, or I don't know what they were thinking. They're like, yeah, that's casino games. That's literally. Exactly. That's what casino games literally are. They're literally that, right? There's dice games where only a couple things win. Everything else loses. And people are like, I'll throw my money down, heck yeah. And you're like, what? I don't understand that. So it's not rigged. You know the rules going in. You just choose to play, right? I guess so, yeah. Some people just like that stuff, right? Okay, so that's the probability. So probability is any outcome of a chance process. Is always a number between 0 and 1, or 0 and 100%. You can't have a 110% chance of something happening, right? It can't go over 100%. When we talk about probability, we always use decimals. When we talk about chances of winning or chance, we say percents, okay? Probability describes the proportion of times the product outcome would occur in a very long series of repetitions. So when we say we flip a coin, what are the chances that I flip a coin and get a heads? We're not talking about one time. We're talking about even more than this, right? Even more. It's 50%, okay? In the long run, that's called the law of large numbers. It says that the more we do something and repeat something, the truth is going to come out. The true probability is going to come out. So if you sit there, play any game, blackjack, a card game, a dice game, if you walk into a casino and play those games, and you sit there for a day, a week, a month, and do nothing but play that, and you're like, I won about 10% of the time. That's the chances you're going to win. It's about 10%, and the house is going to win 90% of the time. Okay? Casinos know that. So that's how they make money. That's how casinos make money, because they know that. They don't put a game out there unless they know exactly what's going to happen when 1,000 people play, right? So People think, oh, well, I'm not going to play 1,000 times. I'm only going to play one. Yeah, but there's 1,000 of you, right? And that's what the casino does. What's the number one rule of a casino? What's their number one rule? Because no, what's the number one rule? You guys ever seen the movie Casino? It's a great movie. Wait till you're 18 to see it, but yeah, it's a good movie.
That's the one where they broke the guy's arms for carrying around a magic?
Yes.
Yeah.
The number one rule of a casino is get them in the casino and keep them playing. Keep them playing. So they'll give you free things, right? They'll give you free things. You want a free drink? You want a free dinner? You want a free room? You want a free this? You know, casinos give freebies all the time. Why? Because the number one rule is to get them in and keep them playing, right? They keep the temperature nice. It's not too cold. It's not too hot. They pump in extra oxygen in there so you stay awake, right? That's why they do it, because they know in the long run they're going to win. Okay?
That's crazy. Every casino.
They know, they're just smart. That's it. That's the thing. This information is not like I didn't go to some secret class to learn this information. It's just probability.
For the casino?
Yeah, it's just probability. Just people are just like, they're just like this when it comes to casinos. They just don't care. Okay? So you can do what you can do. Okay, so we're gonna talk more about it. Don't worry, we'll talk way more about this, but it's just a kind of an intro. That's what probability is. So probability is not one time. So probability is not one time. That's the biggest thing. The probability is not, okay, what are the chances I get a heads? If you say 50%, it's not true, because it's very unstable, right? It's very unpredictable. If I did this 1,000 times, then you're saying 50%. Okay, so that's the main thing here. The second thing is what's called the simulation. Thank you, sir. A simulation is an imitation of chance behavior. There's some behaviors that we can't recreate for ethical reasons, for practical reasons, for financial reasons. We can't create some situations or recreate them. So we do what's called a simulation. It's an imitation, right? When my cousin is a retired, he used to be in the Navy, and he used to fly fighter jets, you know, like Top Gun fighter. That's what he did. He did that for years. He recently retired, but when he learned to do that, they didn't put him up in one of those jets and have him go practice, because those things cost about $100 million each. Each of those things cost that much money. So what they did was they put him in a simulator. They put him in a simulator, which it imitates the air, right? And then when he got good enough, then they're like, okay, now we'll take you up in the air, right? Because why didn't they put him in a plane? Exactly. If he crashes, not only could he lose his life and the life of the person with him, but that's millions of dollars, hundreds of millions of dollars down the drain. And whose money is that? Taxpayer. Exactly. Taxpayer money, right? And that's what they're doing. They're messing, you know, so that could be an issue. So they make a simulator. Okay, so simulation. So we're going to do a simulation together here. Okay. So it's simulation. Really? I would expect that from a freshman. All right. So an example, the chance of contracting strep throat. Okay. How many people have had strep throat?
I don't know what that is.
Then you don't have to raise your hand.
Sounds terrible.
Okay. So the chance of contracting strep throat, I've done it. I've contracted strep throat many times, a few times, is when you come into contact with an infected person, there's about a 15% chance. So if someone in here, obviously not now with masks, but if we were unmasked and you came into contact with someone who had strep throat, there's about a 15% chance that you would get it too. Okay. Suppose that 4 children of a family come into contact with an infected person. So there's 4 children in this family. They all come in contact with one person unmasked. And So we're going to conduct a simulation to answer the following questions. The questions are at the end, okay? Why can't we do this? Why do we need a simulation to do this problem? Exactly. There's a chance we could give people strep throat, right? Why don't I do 20 trials? So I tell the kids, okay, go play with the person with strep throat 20 different times, right? Many problems I can just think of with that, right? So this is what they do. This is how they figure out the chances of you catching COVID. I wrote this question. I didn't write it. I found it 5, 6 years ago before COVID happened. So it's similar with COVID. And that number 15% is way higher with COVID. Okay. So because COVID is a viral, strep throat is bacterial. Bacterial moves a lot faster. Viral moves a lot faster and it's harder to contain. Okay. So that number is way higher for COVID, but it's a good example of how things pass. Okay. So again, when they're trying to figure out how contagious COVID is, this is the kind of thing they do. They don't give people COVID. They find simulations. They do simulations of that stuff, right? Okay, so we're going to use the random number chart. So this is a random number chart. These numbers were generated randomly through an algorithm. Okay, so we're going to do 20 trials. So I just repeated the numbers on the second slide so that you guys don't have to keep flipping back and forth. So the next slide is just the numbers. Okay. There are 5 parts to a simulation. 5 parts. When you do a simulation, you have to show these 5 parts. The first one is we have to assign digits. Assign digits. The second one is a stopping rule. When do we stop? And then the third one is, okay, let's do one trial. One trial, let's do it. And then the fourth one is, okay, let's do as many trials as we need to do. And how are we going to a scoreboard? How are we going to show what happens? And then the last one is a conclusion, where it means answering questions or answering the question we have. Okay, so the questions we have are down here. We have to fill in the blanks. Based on our trials, number of trials, what percent of the times will 0 kids in the family get strep throat? 1 kid, 2 kids, 3 kids, all 4 kids. That's what we have to answer. Okay. Okay, so first thing is we have to assign digits. Assign digits. What do we have to assign digits for? There you go. It goes with the probability. The probability they said is 15% in the long run. So does that mean if I have 100 people go and hang out with someone who has or strep throat, are they 15 of them going to get? No. That means if 1 million people, 10 million people, 1 billion people go and hang out with people who have strep throat, about 15%. That's where we got that number in the long run. Okay, so we have to assign numbers based on we have to assign numbers based on the probability. 15%. Assign digits. You guys know how to assign digits. So what digits would we assign to someone getting it, a positive case? And what numbers would we assign to a negative case, not getting it? That's a one way. We could do it. We could say, hey, if I get a 0, 1, all the way up to 15, that means you got it. You got the disease. And if I get a 16 to 100, you don't get the disease. You got away. You're good. Probably better to do it that way because I don't want to have to do 3 digits at a time because then there's going to be a lot of numbers outside the range. Okay, so let's explain this down in the assigning digits part. So we said 0, 0. Okay, so when do I stop? After 20 trials, right? So when do I stop one trial though? No. After every 4 people. Every 4 people. Yep. Every 4 people, that's going to be one trial because there was only 4 kids in the family, right? So positive, let me keep writing this. Positive case 15 to 99. Negative case. Okay. And we said we're going to stop at one trial. One trial equals 4 what? 4. Why did I choose 4? Out of all numbers, why did I choose 4? 4 kids. Okay, so for one trial, I'm going to 4 kids. Okay.